Welcome. So, we will continue our discussion on link budget. Till now we have seen that how we can calculate the link signal power at the receive point and at receiver point, and the noise which is generated by the receiver, also it is whether it is coming out from any external source. And then we try to see the quality of service in terms of signal to noise ratio. We generally call here as carrier to noise ratio, that is carrier power to noise ratio, and we will try to derive how in terms of transmit power, receive power, transmit antenna gain, the different type of the losses, etc. Let us go to our expression. Our expression last time, if you recollect, it was like this, that in dB terms C by N naught, since we have made it noise power density, so the unit will be dB hertz, not simply dB. It was not simply ratio of two powers, it is dB hertz now. That is expressed in dB as a EIRP, which is dBW, G by T, which is dB per K, and then 1 by path loss, which is 4 pi r by lambda whole square, which is in dB, and of course the Boltzmann constant K, that is 1 by K, dB per K per hertz. Now in this there are a couple of things, are important things are coming out, the characteristics. That is, one characteristic is this one, which is EIRP. EIRP, if you remember, it is multiplication of transmitted power and the transmit antenna gain, and of course the related losses like mispointing and the feeder loss at the power amplifier to antenna, etc. All these things are there in the EIRP. This is the characteristics of the transmitter side. Now there is a term G by T which is coming, which, if you remember, this G is the receive antenna gain, and this T is actually the system noise temperature of the receiver. So this G by T characterizes the receiver, and there is a path which is coming based on the path distance, and the lambda, that is based on the frequency of transmission. So this is the path related loss. Remember, though I am calling it loss, it is not attenuative loss, it is the spreading effect that is coming, that is being seen here. So this is not a KTB type of loss, this is not a attenuative type of loss, this is a spreading loss, though we are using the term loss because it is reducing the power, it is 1 by, so therefore it is reducing the power. Here I made a mistake. Do you see the mistake? I was using ratios here and then dB, and I made a multiplication term. It is not correct. This should be plus, or I can put it as a minus value if I put it up, and this is plus. No, so I should rewrite it correctly. You see the type of mistake generally people make. I also made that mistake. So let us correct it. Of course I corrected it. In dB it is like this. So I will rewrite the whole two expressions properly. One is, when you write in ratio, it will be C by N naught is EIRP multiplied by G by T multiplied by 1 by, let us call it path loss, or let us write the same thing, 4 pi r by lambda square into 1 by K, which is in ratio, and in dB it will be C by N naught is equal to EIRP plus G by T minus 4 pi r by lambda whole square, which is path loss, minus K. So it is in dB term, and unit is dB hertz, because it is N naught, hertz has gone up. Now let us see that importance of EIRP and G by T. What is their content in the EIRP? In EIRP we contain the PT, I write in dB, PT minus the loss at the transmit feeder, that actual power which is appearing at the antenna point. PT is the power amplifier output, and there is a feeder loss. So, actual power will be reduced from this, and then the G, that is transmit antenna on axis or bore side, that is in the maximum direction on line, and of course, it is reduced by the transmit pointing or mispointing, I should say. So, this unit is dBW, that characterizes the transmit side, and the G by T, which is the receiver characteristics. In this, the G is the antenna gain of the receiver on axis. Then there is a loss the receiver by the pointing. Then there is a loss by the receiver polarization mismatch, if you recollect. So, all these things will be put together, and in dB term it is the antenna gain part of that receive antenna, and there is a T, which is the receiver system noise temperature. That includes the antenna noise what it's received, the E cascade, that is the receiver cascaded subsystem system noise, the noise temperature, effective noise temperature, and also the antenna point to the receiver, that receive feeder temperature, which will be appearing as a loss. So, the characteristics of the receiver is found out from the G by T, and remember always this G is not the receiver gain or LNA gain, it is a gain of the antenna of the receiver, and T of course the system noise temperature, and EIRP characterizes the transmit side, which includes the transmit power amplifier and related losses, the transmitter antenna gain and the related losses. So, now we know that a link quality, which is the signal to noise ratio, in other case we say here carrier to noise ratio or carrier noise density ratio, is now listed. Now, we have actually in the satellite two links, uplink, which is earth to space, and downlink, which is space to earth. And till now mostly we are discussing about the satellite which simply bends the signal down. Of course, it translates because of its isolation region, translate the frequency, but the actual signal is going up, getting amplified and coming down. It is normally like a bent pipe. So, the signal power is getting amplified and pushed down in the downlink. Similarly, noise power which is received by the satellite receiver also gets certain gain and comes down. So, at the receiver I see the quality in terms of the signal to noise ratio, carrier to noise ratio or carrier to noise power density ratio, how it should be related to the uplink carrier to noise ratio and downlink carrier to noise ratio. There are two separate things. So, let us try to see that how does it look like. Let us say this is the satellite unit which has a gain, I call it a small g, because capital G we are using for the antenna gains. So, this is the satellite unit. Now, there is a earth station which is transmit and going up to the satellite. So, it is called uplink, that is earth to space. Similarly, satellite is pushing down the link to the earth station, which is receiver station, and it is space to earth, that is why it is called downlink. Always you remember there is uplink and downlink. So, since there is a transmitter involved and a receiver involved at the satellite, and there is a path in between. So, at the uplink we will get some C by n naught, which we will call uplink C by n naught, and at downlink also similarly satellite is transmitting, it has a transmit antenna gain and amplifier. So, it has a EIRP, and a station receiving, it has a G by T, and there is a downlink path. So, it is also having a C by n naught, which is downlink. So, we can write separately, that is for the uplink path C by n naught, let us call only U instead of up, is EIRP of the earth station plus G by T of the satellite minus loss, path loss is dominant, all other losses are there. So, I simply write loss. So, that is in the uplink path, this uplink path there is loss, and minus the Boltzmann constant K, all are in dB, that is why plus minus is applied. Similarly, in the downlink path we have C by n naught downlink, which is now EIRP from the satellite plus G by T. Now, the earth station is receiving, so it is the earth station minus the loss in the downlink minus Boltzmann's constant K. Now, if the same earth station, one earth station is transmitting, say this part of the earth, there is a satellite here, and from here somebody is transmitting and here somebody is receiving. So, the uplink distance and downlink distance may be or may not be same, and then uplink frequency is higher, we have seen as per ITU regulation, and downlink frequency is relatively lower from the uplink frequency. So, lambda is different. So, uplink path loss and downlink path loss, because of their range difference, their frequency difference, they may not be same. Even if the earth stations are co-located, side by side located, still there will be difference, because the distance may be same, the frequencies of uplink and downlink, if they are different, the losses will be different, remember. Similarly, earth station antenna diameter and power which is transmitted is different than satellite transmit power and the antenna. So, EIRP earth station and EIRP satellite in the uplink path and downlink path will be different. Similarly, the receiver characteristics of the satellite and the receiver characteristics of the earth station as well as the antennas, they are different. So, G by T of satellite and G by T of earth station will be different. So, uplink C by n naught and downlink C by n naught are independent things. They may have different value, they may be adjusted to almost same value. So, let us try to see what really happened in totality. What really happens in totality, that is what we should look at it. So, at quality of service we see at the receiver. So, at earth station receiver, the total carrier power received is called C total, let us call C total. What is received actually is downlink carrier. So, it is same as C down. Now, this what is C down? If you remember that we said that there is a uplink carrier going up and there is a satellite gain, that carrier power is amplified by this gain and pushed in the downlink. So, the C downlink is C uplink multiplied by the satellite gain. So, C downlink is satellite gain multiplied C uplink. Similarly, the total noise power at receiver is noise power density. If we say noise power power density N0. So, N0 of the downlink plus the satellite gain multiplied by the N0 of uplink. That means that uplink noise is amplified and coming down. It is received noise is not only the downlink noise, the noise from the uplink is getting amplified and coming down. Though we are getting advantage of the carrier power is getting multiplied by the gain, the noise power, downlink noise power plus uplink noise power multiplied is coming down. So, let us see the resultant what really happens. That is, if we try to say 1 by C by N0 total is, I can write in different way, N0 total, T for total, by C total, which is N0 total by C downlink, because what is downlink is seeing is the total, which is equal to G times N0 of uplink plus N0 of downlink, that is N0 total, divided by C of downlink. I can separate it out, that is G of N0 uplink plus N0 downlink, and this is separately divided by C downlink. We can write it this way. Now, what is this C downlink? Is G times C uplink. So, I can write it G times N0 uplink by G times C uplink plus N0 downlink by C downlink. G gets cancelled. So, which is, I can write reverse, that is 1 by C by N0 of uplink plus 1 by C by N0 of downlink. So, 1 by C by N0 total is equal to 1 by C by N0 uplink, 1 by C by N0 downlink. That is what in bent pipe transponder we get. So, let us write it again for to see our observation. 1 by C by N0 total is equal to 1 by C by N0 up and 1 by C by N0 down. Remember, when we do these type of calculations, this is in ratio, not in dB. This is in ratio. You should do this calculation in ratios. Now, there are certain observations that is coming out of this. One of the observation, let us see what are the observations. You can straightway see that if C by N0 uplink and C by N0 downlink, if C by N0 uplink and C by N0 downlink are made same, somehow we made both of same, it is called balanced link. If I make it a balanced link, what is the effect? You can see the effect, that is for a condition where C by N0 up is same as C by N0 down, then the C by N0 total is half of either C by N0 up or half of C by N0 down. So, that is one of the observation. So, in dB terms you will see it is 3 dB down of, since both of them are equal. So, 3 dB down of that. So, it will be lower than, it is half of that C by N 0 up and C by N 0 down, whichever you take when both are equal. Another observation, it is just like parallel resistance and equivalent resistance calculation. So, the other observation is similar, that is, if the C by N 0 total, that is equivalent resistance, will be lower than the minimum of these two. That is, the observation number 2 is C by N 0 total will be less than minimum of C by N 0 up and C by N 0 down. Whichever is lower, this will be lower than that. So, let us put some numbers, then you will see the fun of it, how much lower. That is very important. So, let us look at some example. Let us put it as example. Find total C by N 0 when C by N 0 up and C by N 0 down, each equal to 20 dB hertz. Then what is the C by N 0 total? That you can calculate. Actually, you should calculate in ratio, but as it is, we have seen it will be half of that, and half of that is 3 dB. So, it will become 17 dB hertz. When they are both same, it will be 3 dB down. So, 17 dB hertz. Let us see another example. Example 2. Find total C by N 0 when C by N 0 up is 20 dB hertz and C by N 0 down is 10 dB hertz. When the downlink C by N 0 is 10 dB down, that is 10 times lower than the uplink. So, downlink is now 10 times lower than the uplink, just put one condition. Then let us see what is the effect on C by N 0 total. So, it will be C by N 0 total is equal to C by N 0 up inverse, C by N 0 down inverse, and we said calculation has to be done in ratio. So, we convert that one. So, it is 20 dB means it is 100 inverse plus 10 dB is 10 inverse. So, result is roughly 9, and sorry, if we inverse is again C by N 0 total, result is 9, which is 9.5 dB hertz. So, now you see it is lower than the downlink, which is 10 dB hertz, it has become 9.5 dB hertz. So, when I reduce this one 10 times, reduction from the lowest one is about 0.5 dB. Let us see, take another example which is more extreme. Let us say take example 3. Find C by N 0 total for C by N0 uplink as 40 dB hertz and C by N0 downlink as 10 dB hertz. So, C by N0 total inverse is now 40 is 10,000 inverse plus 10 inverse. So, C by N0 total will become 9.99 approximately, and that means in dB it will be 9.995, let us say, dB hertz. In calculator you will find some more decimal points. So, now that is lower than C by N0 down by 0.005 dB. So, that shows that in a highly imbalanced link, for highly unbalanced link where uplink and downlink C by N naught vary by 1000 times, 10,000 times or more, then C by N naught total will be approximately equal to the minimum value of C by N0 up and C by N0 down. Out of that, whichever is minimum, it will be approximately. There you can use always thumb rule to do this type of calculation. Where it really happens, let us see some of the practical examples where it really happens. That is one of them. Let us put a satellite here. This is a solar panel, a bigger station and a smaller station. One of the example is satellite TV broadcast, and this is your direct to home receiver, and this is the transmitter by service provider. There are standard commercial service providers are there, and government service providers are there, like Doordarshan, like Tata Sky, like many others, Z, etc. So, this link is a fat link, uplink, and this link is a thinner link in terms of C by N naught. So, C by N naught uplink is very high compared to C by N naught downlink, one of the example. The completely reverse example could be, there is a satellite and you have automatic weather station and you have a large antenna by India Meteorological Department. Uplink is thin and downlink is fat. There could be other examples where VSAT ATM networks are there. So, that could be, I just draw that picture before closing. This is a satellite, this is a hub, and they are VSAT, very small aperture terminals, which you have seen in bank ATM. So, it is a VSAT ATM network. Another example where it is two-way communication. So, this is fat in uplink and downlink, and this is thin in uplink and downlink in terms of C by N naught, So, with this, for the timing we close today's lecture, and we will see what are the other effects that happens over the total C by N naught because of reasons like interference. Okay. So, thank you very much for listening. We will continue this discussion on link budget.